Hello, this is Chengxi from Purdue University. Today I'm going to present my paper, Learning 3D-Aware Egocentric Spatial-Temporal Interaction via Graph Convolutional Networks. This paper was done when I was an intern at Honda Research Institute and collaborated with Yue Meng, Stanley Chen, and Yiting Chen. We believe that in the driving scene scenario, interactions happen everywhere and every moment between road users. For example, in the following figure, an ego car is yielding to an oncoming vehicle. Understanding these interactions, especially how human driver interacts with road user, is beneficial for intelligent automated driving system. Our goal of this paper is to learn an egocentric spatial-temporal interaction model, and we demonstrate that our model really captures the interactions by applying it to the tactical driver behavior recognition task. The main differences of our method with existing ones are the following. First, we decompose interactions into two categories: ego-thing interaction, ego-stuff interaction. Thing objects include those movable objects like pedestrian, cars, and so on. Stuff objects are those traffic infrastructures such as traffic lights, signs, and traffic lines, and so on. Secondly, we incorporate the object's 3D locations in terms of spatial modeling, which is more precise compared to just use 2D pixel coordinates on the 2D image plane. Third, in order to extract features from irregular stuff objects, we introduce a new method known as the MaskAlign operation. In our framework, given the egocentric video frames, we first apply 3D convolution to extract visual features. Every frame is also preprocessed by object detection and semantic segmentation, obtaining the object bounding boxes as thing object and semantic binary masks as stuff object. We use ROI-align to extract features from object bounding boxes. We designed MaskAlign to extract features from irregular shape binary masks. And then we construct two graphs to model the interactions. Ego-thing graph in the upper branch is designed to model interactions of ego vehicle and movable traffic participants. The lower branch is called ego-stuff graph, which is representing the influence that the road infrastructures have on ego car. When we're modeling the spatial relations between every pair of nodes, we do not only use their appearance features, but also the distances in 3D coordinates. Information is passed to each other by graph convolution operations. By now, the ego node is updated and fused with information from other objects. We use this frame-wise ego feature and feed it into a temporal modeling module to form an interaction representation. In the temporal modeling module, we tried max pooling, average pooling, and multi-layer perceptron. We will show the ablation study later. In the end, we aggregate the features from the I3D branch and the graph convolution branch as the final egocentric representation, and we use it for driver action recognition. In order to validate our model, we apply it to action detection task, where the input of a long untrimmed video will be processed and generate predictions of ego car tactical behavior at each time frame. We evaluate the proposed framework on the HDD dataset, the largest dataset that provides 104-hour egocentric videos with frame-level annotations of tactical driver behavior. Here I'm showing the quantitative results in action detection task, and we use the per frame mean average precision as our evaluation metric. As we see from the table, our model improves the overall performance by 1.6% compared with the I3D baseline. While the overall MAP does not seem to be very impressive, we observe a 3.9% performance boost on the line-related classes: line change, line branch, and merge. This improvement showcases the effectiveness of modeling interactions between ego vehicle and traffic lines. Similarly, we extend our framework to multi-head classifiers to simultaneously predict goal-oriented actions and causes defined in the HDD dataset. So here are the results of cause layer. 6 classes from cause layer are designed to explain the reason for stopping and deviating actions. For example, deviate for parked vehicle. This is a good example of ego-thing interaction. Our model achieves 6% increase in overall MAP. We also conducted an ablation study to investigate the contributions from each module. We decompose our model into 3 components and find out the following conclusions. First, 2 graphs are necessary. Second, embedding 3D distances provides better spatial modeling. Third, max pooling performs best among the 3 temporal modeling designs. Other advanced temporal modeling, such as a temporal convolution network, can also be applied in our future work. We selected some interesting examples for visualization. In the first example, our model predicts the ego car is yielding to crossing pedestrian before turning right. In this clip, it is first detected as taking a left line change and then stopping for the red light. And then, this is an example the ego car first yields to the crossing vehicles and takes a left turn afterwards. To better understand what the model learns about the interactions, we text out the learned interactive weights from GCN. We pay attention to those weights between other road users and ego vehicles. As we see in the visualization, when the ego car intends to turn left, it pays strong attention to the crossing vehicle. Here I'm showing more results. In the last row, when the ego car is doing some line-related actions, our model learns a strong attention weights between the traffic line and the ego car. We also generate another form of visualization from a top-down view. In this example, the cause layer prediction is deviating for a parked vehicle. We're curious about how the learned graph looks like in this case. So here, we visualize the ego thing graph. In the frame, there are 6 cars and 1 pedestrian are detected, and our model learns the affinity matrix on the right. For convenience, we translate it into a top-down view, in which our model learns that the car 1, car 2, and car 3 has interactions with car 4, and the ego car has interaction with car 5. Car 5 is exactly the parked vehicle that the ego deviates for. In conclusion, we propose a framework to model complicated interactions between driver and road user using graph convolution networks. The proposed framework demonstrates favorable quantitative performance on the HDD dataset. Qualitatively, we show the model can capture interactions between the ego vehicle and the staff object and the ego vehicle and thing objects. For future work, we plan to incorporate temporal modeling of thing objects into the proposed framework, as it is an important cue in interaction modeling. With that, the framework will enable tactical behavior anticipation and driver behavior modeling, and potentially trajectory prediction of thing objects. Thank you for attending my presentation.